is John Pritchard. I've been with ESO for almost 20 years now. I started with at Lucia as most notably there, I was the instrument scientist for Ferros. In 2006, I moved to Garching, where I became the UVES QC scientist, which those duties I did until 2012 when I moved to the user support department. And since then, I've been in the user support department, being the primary user support astronomer for UVES, amongst other instruments, flames as well. I also support X-Shooter and Espresso and Force. Yeah, okay, so the participants who requested this session, as I said, is Murat, Esha, and Andre. You three, please feel free to turn your microphones on and participate and ask questions at any time you want. If you're doing this in parallel, if you're running ESO-REx on your own computer, if you want to show me something or we can discuss something, you can share your screen and you can show me if you have a problem or anything like that. So the idea is to try and be interactive as much as possible, as much as we can, given the format that we're in. Other than that, I will run through the UVES demo data, run that through the UVES workflow, and try and point out as much as I can along the way that I hope will be interesting and useful to you as we go. It would, however, be useful if the three participants could tell me just how much experience they have with UVES and or the workflow in the past, and ESO Reflex in general, whether they've had no experience at all. So this is a sort of first time experience, whether you've used it a little bit, but you're not really very comfortable with it, or if you've used it a lot and you're quite comfortable, then you want to get expert user or something like that. So if you wouldn't mind, unmute yourself and just let me know what kind of user you are. Can we start with Murat? Does anybody hear me?
Yeah.
I can hear you.
Oh, okay, good. Esha, would you like to start?
Yeah, I haven't not yet used ESO Reflex or UVES data. I am about to start. So in future, I will probably use UVES for my science. So yeah, I have no experience so far with ESO Reflex or UVES data.
Okay. Well, anybody else? Andre, would you like to?
It's my first time using UVES Reflex as well, so
Okay.
I'm starting studying some type of stars, and I need to use the UV, so UVES is the best choice.
Okay. Good. Murat?
Hello, John. Could you hear me?
Hi. Yes, I can hear you now.
Sorry, I have a bad connection. I have a bit experiences, but not much. So hope that this workshop gonna be quite useful. And thank you very much for this workshop.
Okay, no problem. I should also point out that Sabine Moller, who is participating in this meeting, is also going to give a session tomorrow on using Reflex, a general session. So hopefully I won't say too many of the things that she's going to say, but anyway, but since we are here, we have to, and she hasn't spoken yet, we have to do a certain amount. Right, so I hope you can all see my terminal window, which I'm typing in now. Normally, it's simply enough to get started with ESO Reflex. Let me first say that possibly the most difficult part of using ESO Reflex is getting it installed. I get lots and lots of tickets about problems with installation, and much fewer tickets actually about problems with using it. So if you have at all any problems with installing ESO Reflex, send a ticket to usdhelp@eso.org, and most probably it will come to me, and I'll do my best to make sure, or do my best to get ESO Reflex installed and running on your machine. So normally it's then enough, once it is installed, to type ESO Reflex, and that'll get you started. Of course, you can type -H to get some help on it. And there's debug modes. There's lots of information about customizing the workflows, which we'll get to. A nice feature is that there is a non-interactive mode. So you can use ESO Reflex perhaps to, if you have lots and lots and lots of data, if you have, you can use ESO Reflex perhaps to check that interactively, to check that it's reducing the data in a way that you think is correct. Maybe you need to adjust some parameters, and once you're happy with that, you could then run the workflow on a large set of data non-interactively, so that it just runs through, and then at the end of it, you can look at that data as well. We hopefully get through to the point where we can, where I can show you how to do that. You can also, a very important command is that you can list with ESO Reflex -L all of the workflows that you have installed. This is useful because you can then specify which of the workflows you want to use as you start up ESO Reflex. So normally then, if I wanted to use the ESO Reflex with UVES, I would simply type ESO Reflex and UVES, and it will start up. It always takes several minutes, which is a bit annoying, but there you go. So ESO Reflex is a tool that was originally built by the Austrians, so Austrian astronomers, as part of their payment for joining ESO. It's built around a workflow system called Kepler. So it's a layer on top of Kepler. So it uses many of the standard features of Kepler, and it uses some special features that ESO has itself, and the Austrians who prepared the original version that they developed specifically for use in running ESO pipelines. So when it first starts up, it should look something like this. If you started the UVES one, you can immediately see several parts to the screen. On the left here, you have some folders and looking things and searching possibilities. There's a zoom of the whole screen in the lower left corner, and the main body of the workflow is represented by what we call the canvas here, which has some information about how to use it. It has some parameters that mostly don't need to be touched, and I recommend not to touch them. And then it has some parameters that allow you to control a little bit how the workflow is run. The first thing I can tell you is you can close, just at the top here, there are two little arrow buttons, and you can close off that part. You don't need that unless you're going to modify or create your own workflows. Then you can click on the zoom button and make it a bit bigger and a bit more comfortable. You can see different things. So I'll now zoom in a wee bit more. Whoops, daisy. It's a little bit touchy if you touch the wrong buttons on your mouse. So what I wanted to do was zoom in a little bit, and then the best way to move around is using the sliders. At the top left, we have the workflow instructions, which just go through basically what I'm going to tell you. At least that's the very basics of it. In the middle, we have a section on the setup directories. When you install ESO Reflex and you run it from the command line, as I did, just ESO Reflex UVES, or whichever instrument workflow that you choose, it will be set up and configured to use, to work in a directory that is a subdirectory of your home directory. That's the root data directory. So that's where it's going to write all of the files that it's going to create along the way. And it will use the data that it will try to process will be the demo data that comes as part of the packages, which is the raw data directory. Normally, then, everything else below there, you don't need to touch. You might want to change the root data directory. For example, I usually like to keep all the processing for a specific project or a night of data or something together. I don't want it all mixed up. If you leave it this way, everything you ever do with ESO Reflex will all go into that directory. So all the different instruments, all the different projects, everything goes into the same directory. Personally, I prefer to keep things separate. And so then that is the directory that you need to change, the root data dir. And when you want to reduce your own data, you need to change the raw data dir. We'll come to that a little bit later. The next thing to discuss a little bit are these global parameters. The first one is the recipe failure mode, and this determines what happens if one of the recipes fails, whether it will just continue and try to keep going anyway, whether it will stop, or whether it will present you with a question whether you want to continue or stop. Another parameter is the erase dirs, so this allows it to if you set that to true, then before it does anything else, it will remove all of the data directories that may be there from a previous run execution of the workflow. The disadvantage of that is that ESO Reflex has what's called a lazy mode, whereby at each time it wants to run a recipe, it first checks whether all of the input data and parameters are the same as something that it's already done. And if so, then it simply says, oh, well, I'll use the results from that previous time that I ran that and move on to the next step very quickly. So that's very useful if you want to come back after having reduced the data once, if you want to come back and try and change or optimize the reduction in some way. There's a parameter for the FITS viewer. By default, it's set to a tool called FV, which comes from the HST. You can also set it to things like DS9 or SkyCat or things like that. Basically, it should be anything that allows you to load up a FITS image. There's a parameter called global plot interactivity, which by default is set to true. I'll talk about that in a minute. The select data set method, also interactive, and the product explorer mode, whether it's triggered, which is what we see at the end of the workflow. I'll come to that as well in a minute. So those are the things, typically the things that you set once, and then before actually running the workflow. There is another important one here, which is the maximum number of flats that the pipeline can handle. This is determined by the amount of RAM that you have in your machine. The more flats that you try to combine into one master flat in one step, the more memory it requires. It's configured such that a machine with 8 GB of RAM should be able, in most cases, to handle up to 12 flats. In most cases, well, the standard calibration plan foresees, in any case, only 5 flats each time. So most of the time, you should only be trying to process 5 flats simultaneously in one set. You'll only have more flats than that if you've specifically observed more flats. If for some reason you need very high signal to noise in the flat, and you specifically requested special calibrations to have, say, 50 flats taken or something like that, which is pretty rare. And there is another parameter, which is the global reduce flat field method, which is controls whether the flat fielding of the science is done in pixel space or in extracted space. So whether you extract first the science and then flat field it, or you flat field it and then extract it. And this has certain implications in different applications, but it's a little bit more detailed than I want to go into today. So those are the parameters and the controlling variables for the workflow. The workflow itself is this area at the bottom, which is broken up in the case of UVES into 5 basic steps. First, we organize the data and select which ones we want to process. Then we create master calibrations, do the wavelength and response calibration, and finally extract the science spectrum and organize the output. You may notice that, so these little green things are what we call actors, and they can be simplistic things. You can double click on them and you can configure them. I choose something a little bit more complicated. Some of them can have many parameters, so you can adjust also the parameters of those. Or some of them are quite complicated and you can open them up, and they themselves are mini workflows, if you like, that consist of actors within actors. So this is a typical one for a pipeline execution, where it allows you to go around and around in circles as you interactively adjust the parameters. One of the final things I want to say here at this stage is that there's also these orange squares around 4 of these actors. This indicates that these actors have a graphical user interface. So you can get a Python window that pops up, and it will allow you to adjust some of the parameters of the workflow of the recipe and re-execute the recipe to maybe get an optimized result or something like that. In the case of UVES, the first 2, the spectrum locator and the wavelength calibration, are by default not active. So as the workflow goes through them, it won't open a GUI for those steps. You have to configure those specific actors in order to actually get them to show up. And I'll show you how to do that in a minute. The second 2, the instrument response and the spectrum extraction, are by default active, and they will cause an interactive window to pop up. That is controlled by this parameter that I mentioned earlier, the global plot interactivity, which is by default in the UVES workflow set to true. So if you want to turn off that interactivity, then you simply double click on that parameter and set it to false. And then the workflow would go through without any interaction at all, because those are the only 2 user interactivity that are normally active. So for demonstration purposes, of course, not very interesting just to sit and watch a workflow do nothing. So I'll turn that back on. Now, the other thing I want to say is that in preparing for this tutorial, for this hands-on session, I discovered a bug in the workflow, or more precisely in one of the Python actors in the wavelength calibration Python interactive script, in fact. And so as it is, the currently publicly available version has a bug in it, and it will crash the workflow if you run it simply like that. So I installed this morning and quickly fixed the Python script in my local version. So I need to run it, I need to restart ISO Reflex using my local version, which is simply installed here. I'm also going to tell it that I want the root data dir to be in the current directory. This is what I mentioned before, keeping things separate. So I'll do everything that I'm going to do with this demonstration in this. All the files that I produce today will go into directories of this directory. And because I'm using this local version, I need to tell it to, or I want to tell it to point at the version of the data demo that I've got installed via Mac ports. I could do that, but maybe it's more instructive that I actually do that in the workflow. So I'll get rid of that option. There we go. So I've just got the name of the executable. I'm telling it I want the root data dir directory set appropriately, and I want it to load up the UVES workflow. Enter. So we just need to wait for Reflex to start up again. Does anybody have any questions at this stage? We're only 9, 8, not counting Sabine. So I think it's fine. If anybody in here watching has any questions at all, just turn your microphone on and ask as we go. Okay. Okay, so we have the workflow. It looks just like it was before. Again, I'll get rid of that window, make it as big as it can. So by default, as I mentioned, the raw data directory, I just zoom in a wee bit here, is pointing at where it should have been if I had installed the data demo as part of the installation script. But as I mentioned before, I actually ran out of disk space. So I want to point it to the demo data that's already installed via the MacPorts Package Manager version. So I simply double click on the name. I think it doesn't work if I double click. Oh, it does work. So you can double click anywhere on the name or the value, and you get a pop-up window where you can edit the parameter of the canvas. And then I just browse via the normal thing to the place that I want, to the directory that I want to use. So I'll have to cancel that, make the window a little bit smaller so I can see what I'm doing. I'll put the workflow into the background, and then I'll go back up to the command I had before so that I can see the directory. Okay, so it's this one here, op local blah, 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 blah. So we'll do that again. So browse, go to opt local, libexec to there, and then from there I can get it to ISO, stable, CPL, share, ISO pipes, data demo, UVES, and UVES. Okay, so this would be the same process if you had all of your own data stored somewhere on your disk. You just navigate to the right place, set that for raw data dir. The only restriction on this is, there's two restrictions actually. Not a good idea to have any spaces in the names of the directories, neither of any of the directories that you're using, nor of the directory that you're working in. And this raw data directory must not be a subdirectory of root data dir. Otherwise, it gets a bit confused between what is a raw file and what is a product file. But apart from that, it can be anywhere on your disk. Okay, so we're back to the full size. There's a feature of Reflex, which is that it can highlight with a little red square around the box that you'll see in a moment, which step in the workflow it's up to. Unfortunately, it's not possible to have that enabled automatically when the workflow starts up. So each time you start the Reflex workflow, you have to manually enable it each time. You do that underneath in the Tools menu, and it's the Animate at Runtime function. Set it to something like 100 milliseconds. Okay, that. Oh, actually, let me disable it just so that you see the difference. Otherwise, it's maybe not. So it's off now. I try running it, which I do 9 times out of 10. I forget to set it up. And you see we've got a window popping up, but there's no indication that anything happened apart from we press the button. So we'll stop it there. We'll enable it again. Animate at runtime, 100. The thing. And try it again. And this time we get this little red square appearing around the actor that it's actually in the middle of executing. So with the UVES demo data set, it comes with 9 data sets. Only 8 of them, or 1 of them is ghosted out because it's incomplete. We can check on that. You can select it, and then you can inspect the highlighted. And it will tell you here that the data set is incomplete because there are 2 types of files that are missing, a master flat for the red lower and the red upper chip. So in the demo data set that comes with UVES on purpose is incomplete for this data set, just so that you can see what it looks like. And you can see, and it tells you which files are missing, and therefore which files you possibly need to go to the archive to try and find. You can also explore the associations that have been made. So here's our original science, and these are the files that have been associated to it. So you can see that it's been associated, these 5 bias files, which come from 2009-04-13. It's also been associated the dark, which comes from November 2008, and it's been associated a different set of biases. And the Reflex workflow will handle all of that. It will process the 2 separate biases separately, and then process the dark with the bias that's associated to it. And then the bias that's associated to the science file will be used by the science file, etc. So we can continue at this stage. Normally, when we started up, having never run this data before, all of these data sets would have been selected because they are by default ready to go. In preparation for this workshop, I've already run the data sets through so that I can take advantage of lazy mode and we don't spend all of the time waiting for things to happen. I can actually show you things. And so normally it would be like this, and you would simply press continue. You can also, but just before we do that, you can do things like deselect all, and then within here, there are the possibility to select specific data sets depending on which ones you want, the ones that have already been reduced, or all of them, or failed ones, or if you've added some data, if you've already run the workflow on some data, and then you go back to the archive and get more data and put it back and put it into the directory, then they will show up when you run the workflow again as new files. So you can select just those and do different things. So let's just, for the moment, we can also inspect, of course, a data set that is complete. So here there's no message about anything missing. And again, as you can go through and see, for what it's worth, all of the files that the data set that the science requires in order to reduce the data. Right, so let's just pretend we only have one data set for the first time. So whichever one is ticked here, whichever one or ones are ticked here will get reduced or processed, and we simply press continue, and the workflow then proceeds. So it's going very quickly, as I mentioned here, because it's able to use lazy mode because I've already run this data through the pipe, through the workflow. So it usually takes I don't know, maybe at most 1-2 minutes to at most 5 minutes. Obviously, it depends on the CPU in your computer, etc. But it's fairly quick. It's a matter of minutes in general for all of the UVES recipes to complete. There are differences. For example, the espresso pipeline takes a lot longer, typically reducing all of the calibrations and the science of one espresso file can take upwards of an hour, perhaps 2, again, depending on exactly how many input files go in and how powerful your computer is. So in any case, it ran through rather quickly. Perhaps it was a bit too quickly for most of you to see. Or some of you to see. And it's finally arrived at the spectrum extraction. You may notice it didn't stop at instrument response, where I claimed there was an interactive GUI. And the reason it didn't stop there is because this particular data set didn't have any standard stars associated with it. That's valid. It's less preferable, of course, because then you don't get a calibrated flux spectrum, but such is life. The flux calibration is not part of the UVES calibration plan. However, some flux standards in certain standard modes are taken on a semi-regular basis, approximately once a week, and sometimes as often as possible when the conditions are good. And But these are taken for monitoring the health of the instrument. But if you happen to be using one of those standard modes, then you can use the standards to go with it. I see I have a question from Sabine.
Actually, wait a minute. Can you hear me?
Yeah. Yes, I hear you.
Actually, less a question than a comment. I must admit, I haven't listened closely, but did you just say that by default, Calselector does not deliver flux standard stars?
Yes, it's an optional.
Okay, let's say by default, it does meanwhile deliver flux standard stars, and the response calculation has been activated because we have very much improved the flux calibration. And this also means that you should be careful if you're working with data you downloaded before, let's say, roughly May this year, because then you may still have old master response curves that are not really good.
Yeah. No, just to clarify, you'll get a flux standard if there is one, an appropriate one for your data set.
Yes.
As I mentioned, depending on what mode you use, etc., there may not be any available.
Exactly. So as I said, I didn't listen closely. It was just the phrase flux standard that suddenly triggered my reflex.
Yeah.
Okay.
Great. Okay. So we may actually need to update then the demo data set, because I think it's still using the old master flux standards.
I thought it was updated, but maybe you can have a look, and if you're not sure, let me know and I will check.
Yep. Okay, great, thanks. So here we have our first interactive window, GUI window. We can maximize it and we can see things a bit more clearly. We have several panels where it's different things are displayed. So of course we have the spectrum itself. In this case, it's just the extracted raw spectrum, non-flux calibrated because there was no standard star. And then we have several other diagnostic panels, which tell you a bit about some of the properties and in principle the QC parameters that have been extracted from the data. We have the signal to noise that's been calculated at the center of each order, the center of the blaze function of each order, the forward half maximum of each order in pixels. We have a parameter that's called ripple, which is we noticed that that the pipeline introduces some artifacts. Which becomes especially obvious when you have very high signal to noise spectra, and this was 10 years ago, even longer probably. And as a result, we implemented something that's called a virtual PSF, and this allows let's just to cut a long story short, we've implemented various techniques to try and mitigate this ripple effect. If you hover over, it doesn't tell you in the help for the plot, but essentially, as long as this parameter is below 5, then the spectrum is in good quality, and the ripple parameter is probably unnoticeable. If it goes above 5, then there are systematic artifacts in the spectrum, and you should try to adjust the reduction parameters to try and mitigate that. And if you have trouble and need help with that, then contact USD. And then you have finally the central position of the object in the slit along the length of the slit, and that's again in pixels. You can see that it's not that it varies across the order, which of course corresponds to wavelength, and that of course is because of atmospheric dispersion. Right, this is a standard matplotlib graphical user interface. So it has up here a set of tools with which you can manipulate the plots. In particular, it has a zooming function, so you can zoom in on features that you find particularly interesting. So this line, for example, you can select the arrows, and then you can move around the spectrum. And of course, it also means you can do that in any of these panels with plots in them. You can adjust parameters like how much space is on the left, etc. And you can even save the image as I think it's a JPG or a PNG to disk. You can use the arrows to go back, which will move the spectrum. So it keeps a history of all of the manipulations you made. So you can go backwards and forwards between the manipulations you made, or you can just go straight back to the default setup. So you can explore a little bit the reduced spectrum straight away, and through that determine whether you think it's good enough or not, or if you need to do some work to try and improve it. If you do feel you need to do some work, then you need to adjust some of the parameters of the recipe. Unfortunately, this worked much better when we were still using Python 2 and the old version of the widget library. Since we upgraded to Python 3, we have this awful property that this part of the window becomes very wide because of this part down here where it lists all the files, and it makes it difficult to see this part up here, which is where you can adjust some of the parameters. So the parameters are grouped into different functionalities, parameters to do with the extraction, to do with the rebinning of the spectrum, and some other parameters. Each one has its own help. So if you just hover over the parameter, it will tell you what it means. And these help messages are essentially the same messages that you get if you use ESO-REX, which is the command line version of running the ESO pipelines. Let me mention quickly, ESO pipelines run in ESO-REX. Reflex is simply a graphical user interface that, amongst other things, runs those pipelines in ESO-REX. So it does a lot of other things like giving you plotting, etc., doing the organization and classification and association, which is an incredibly handy thing to do for a pipeline. But ultimately, they are using the same pipeline recipes. So whether you're using Gasgano, which is the sort of predecessor of ESO-Reflex, whether you're using Gasgano, ESO-Reflex, or ESO-REX, you're always using the same actual pipelines to process the recipe, the data. So if you needed to adjust anything here, this would be where you would do it. So you could say maybe your data is 2D, and you want to, so you've an extended object, so you actually want to reduce it in 2D. You want to get the 2D extraction, so you would change the reduce extract method to 2D, and then you need to rerun the recipe. So here you have 3 buttons that allow you to control what's going to happen next when you're finished with this interactive window. Either you continue the workflow and go on to the next step in this process, which, given that this is at the end of the processing this science file, it will now then start the next science file. Or you can rerun the recipe if you've made some changes. You can click on help to get some help, which I must admit I haven't read very often, and it may or may not be terribly useful. If you're happy with the parameters that you selected and you've got more data to reduce, but you don't need to see this interactive window anymore, then you can disable this window in subsequent for subsequent data sets. So it'll just do this pipeline step without having the graphical interface. And if you've changed the parameters and you think, well, that's the set of parameters I need to reduce my data, and I need to use them and not change them each time I get back to the step, then you can set this parameter or check this radio box to use these parameters for all the subsequent, the reduction of all the subsequent data in this run. For the moment, we don't want to do any of that. We just want to rerun the recipe in 2D mode. So we click on rerun the recipe. This will take a few seconds because I didn't pre-prepare this, but it's not long. It's a few seconds. So we have a few seconds again. Does anybody else have any questions at this stage?
I have a question.
Yes.
The spectrum you get here, which is extracted spectrum, has it taken into account the atmospheric absorption, or it is the raw spectrum?
It is the raw spectrum. So the peculiar shape that you see is partly due to the atmosphere and partly due to the spectral energy distribution of the flat field lamps.
Okay.
Now, am I saying, if you, in order to have a calibrated spectrum that accounts for the atmosphere, then you need to have a standard star as part of the, or a response function as part of the input data set. If you don't have that, then you'll get something that looks funky, like you saw, a very peculiar looking spectrum. Okay, so in the case of 2D, it's a limitation of the UVES workflow that although the pipeline can process these data, the interactive window doesn't actually know how to display them. So you get this very helpful window where it simply tells you that the recipe has completed, but it can't actually find any kind of product that it knows about, so it can't display anything. So it, if you have 2D data, the use of this workflow is less than if you have normal point sources, but at least it does all of the association, does the processing. So you can do all the processing here, but you will then have to have some other tool beyond that to be able to look at the data and see whether it's what you need. So for the moment, we'll just put this back to optimal. You might imagine that you can just now press continue workflow, but if we want it to actually take into account the fact that we put it back to optimal, we need to rerun the recipe again. So one more time, since we've already done that, it's very quick. And we're back here, which we were at before with the plot. And now we can just continue the workflow. It comes to the end of the workflow. If we had selected more than one data set at the beginning, then it would have gone on and gone back to the beginning, or at least gone back to master bias and continued with processing the next image. Instead, because we only selected one, it's now presenting what is called the Product Explorer, where we can, surprisingly enough, explore the products that have been produced by the pipeline, by the workflow. And we see here that the 8 complete data sets have all been executed, exec, at least once. And I've actually processed the first data set 5 times. That's just in preparation for this tutorial. You can expand these and you can see each execution. It's time-stamped with when the processing was started. One of them failed at some point, but the rest have completed successfully. And if you select one of them, then you get the list of the files that it has, the product files that it has produced. In this part, and you can click on any one of those and it will show you the header keywords of that file. Let's see, we want the reduced science point product. You can go into that. So these other ones, you have the error bar, you have the merge sky and the order extracted. So these are different final products. But the final one-dimensional spectrum is this red side point product. And that consists of various other things. So inside that, you can explore further and you can see exactly which file it produced and which files went into producing that science product. And you can further explore each one each time and eventually get down to the raw files that went into producing that product. An interesting feature is that you can right button click and you get a contextual menu where you can do interesting things like go back to displaying the pipeline results. So if you click on that and select that, it will eventually reopen the Python interactive window that we had just a few minutes ago as part of the workflow. Now, of course, we're outside the workflow now, so changing anything and rerunning the recipe won't actually do anything. It's only displaying the final results. But you can still do things like interactively examine the spectrum and check for the signal to noise and things like that. So this is interesting in a sense if you run the workflow in non-interactive mode. So you turn off all the interactivity, you run all the data through, which maybe takes several hours depending on how much data you have, and then you can interactively explore the data afterwards without having to sit there and wait for it at each step. So that's maybe, if you have a lot of data to process, it's maybe the best way to have a first look at the data and whether the pipeline has done a good job. And I can tell you that the UVES pipeline, UVES was one of the first instruments at Paraná, and its pipeline is extremely stable and robust, and it very seldom fails. If you manage to get some data that fails, then it's really an exceptional event, and you should contact USD as soon as possible, probably. The other point is there's a lot of artificial intelligence built into the pipeline that adjusts, for example, the extraction method depending on the signal to noise that is in it to optimize which extraction method is used depending on the data and so on. So it's very robust, and in all honesty, there's although you have the possibility to adjust some of the parameters of the workflow, there's not really very many that there's not much you can do to improve it because it's already so good just with the default parameters. When you're finished exploring, you can continue, and that will essentially end the processing of the workflow. And you can see that because now the stop sign is showing rather than the play button. Time has flown, as it always does in situations like this. So we've got about 10, depending on 10 to 40 minutes left to do a few more things. So we'll start it again, unless anybody has any questions at this stage. Before I do that, I'll stop it at this point. So now I want to see all of the interactive windows. So I'll configure first the spectrum locator, and I just turn the interactivity on by setting the enable interactivity variable to true. And the same with the wavelength calibration actor. Set that one to true. And start it again. And this time we'll process the second data set because I know that that one has an instrument response, has some standard star data, so it will give us an instrument response. We press continue and let it do its work. Note that, as I mentioned earlier, it can be that the different parts of the calibration cascade have different sets of calibrations from the science spectrum. So for example, if the standard star spectrum actually comes from a different night or from the beginning of the night compared to the spectrum at the end of the night, it's quite possible or probable that it will have different biases and or wavelength calibrations, etc., from the science. And so at each step where there is an interactivity, it could be that you actually are interacting for several examples of the same type of file. So anyway, this is the UVES spectral format. The format, or as it's called, format check. So this is an image that is taken with the slit closed down to basically a pinhole, and it allows the pipeline to establish where the spectra are. So the UVES pipeline runs on what's called a physical model. So it has built into it for each wavelength setting, etc., where a set of equations that predict where the lines should be for every setting of the instrument. And as a result, it then goes and searches for the lines that the emission lines that it's expecting at those places. You can control the box size that it's looking in. These parameters up here in the left, by default, uses a 40 pixel by 40 pixel box size. and it tries to find a line in that point, and if it finds an emission line in that point, then it's decided it's located the line. And by doing this for all, well, several hundreds of lines in the image, it then establishes the format of the spectrum and the data, which it then expects to be the same throughout the whole calibration cascade, which is why all the calibrations are taken in a certain sequence and taken together to go with the science, because that defines what the spectrum should look like for that night. So here we can see, for example, that so this, by the way, is a perfectly good format check. The general pattern that we see here, that most of the lines in these two top plots follow a fairly smooth distribution. This is perfectly normal, and this is absolutely fine. You can see that they are not at zero, either one. The mean is not at zero. That just means that the whole spectrum has shifted slightly relative to where the physical model predicted it would be. That happens for many different reasons. It can be that there's been an earthquake at Paranal, and it shakes the whole instrument, and everything in the instrument has moved slightly, and it can move where the spectrum falls on the detector, like so. It can just be many different effects. The earthquake is the only one in general that is liable to lead to a problem. And there's only generally going to be a problem if the difference becomes so large that it's larger than 10 to 15 pixels. In, what was it, 6 years as the UVES QC scientist, I never saw it get so far out that the pipeline couldn't cope. As I say, the pipeline is extremely robust, and it can find and locate the spectrum in a wide range of offsets. We could just, for example, nonetheless, adjust the trans X and Y parameters, which basically we're telling it how much the spectrum has been offset from its expected position. And for those, we can use the mean values of the X diffs and the Y diffs. So if we set trans X to minus 2.648 and trans Y to minus 2.48, and then we rerun the recipe, then we can see now, and that again, I did not pre-prepare that, so that was computing in real time. So you can see the recipe is very quick to complete. And now we can see that the differences are almost, well, it's still a little bit off. On the X diff at least. The Y diff is very close to zero, but X diff is still interesting. And that's probably because of the large scatter in this case. But having said and done all of that, it's really not worth the trouble, because the pipeline is so robust. So even with those parameters set as zero and the differences we have there, absolutely no problem for the pipeline to run through as it is. In fact, if you do the same exercise with the first data set, you'll see that the Y trans, I think it is off, but the trans Y is off by about 11 pixels. So you can set 11 pixels and or minus, whichever one it is, minus or plus or minus 11 pixels, and it will bring it back to zero. But again, it doesn't make much difference down the track. Okay, so we put back the default parameters, we'll rerun the recipe, and we get back to where we were before, and now we'll continue the workflow. The other parameters, the other displays are just these predicted positions. So in fact, what is being plotted here is the difference between the predicted position and the measured position of each of the lines, versus in different cases the X coordinates, the Y coordinates, and X diffs versus Y diffs. And then finally in the bottom right, it's a kind of simple representation of the CCD itself and where it found the points. And so the blue ones are the ones that have been accepted as valid points, in that the difference between their positions was significantly less than the threshold, and the red ones are ones that have been rejected for whatever reason. Right, so we continue with the workflow. We have a systematic, the majority of the points are systematically on a smooth distribution, so everything's fine, no problem. We can continue the workflow. The order def and the master flat actors don't have interactivity, generally because once you get to this point, once you've got a robust location of the spectrum, it's very seldom that these steps fail, and the need to interact is very low. Also bear in mind that when you download data from the archive, if you select some science data and then you use CalSelector to give you the associated calibrations, these are calibrations that have already been certified by QC and Garching. So they've all been run through the pipeline, and if there were any problems with using the standard parameters, they would have been evaluated then, and if there was an actual physical problem with the data, then it would have been rejected, and CalSelector will not give you any calibrations that came from QC rejected data. Okay, so here we are with the wavelength interactive GUI. Before I continue with this one, does anybody have any questions at this stage? I see Esha has her hand up.
Yeah, you just said that the calibrated files will be viewed. I mean, if it is not a proper, then you are not going to provide that. So it is for the raw data as well, or it's for the processed data?
So QC gets all the data from the observatory, and it processes it and creates master calibrations. It then evaluates whether the data is correct, whether it passes quality control, and if so, then the master calibrations that came from those input data, so from the 5 biases, for example, are then archived into the Science Archive facility, and that data is then marked as having passed quality control. If it fails quality control, the master calibration is not ingested into the archive, and is not ingested into the archive. So then what CalSelector does when you select a science file is it looks within the archive, if I get this right and if I remember correctly, it looks in the archive for master calibrations, because only certified master calibrations are in the archive by definition. Then, depending on whether you asked for the raw data or the master calibrations, CalSelector will deliver either the master calibrations that it found to go with that science data, or the raw files that those master calibrations were created with. Now, for the UVES pipeline, it does not know how to handle master calibrations coming from the archive. So to process UVES data, you must always get the raw data. This has been, the use of master calibrations has been implemented for a few of the pipelines, in particular Muse, I know it's been done for. And I found out today there's also at least one of the KMOS recipes that does that. I think, one of the Gravity recipes that can handle that. So we will be doing that eventually, but for the moment, UVES raw data only. Okay. But you can be sure that the raw data you're getting corresponds to certified calibrations.
Okay. Okay. Thank you.
Okay.
Yeah.
Okay. Okay. So here again, we have several panels. It lists the number of lines that were detected, the number of fitted lines, and the final number of lines it actually accepts in that are where the error is smaller than the threshold, and you see a plot of that in this lower panel, in the lower right panel, and you can see the blue ones are the ones that have been accepted, and the red ones are unaccepted, and basically you want that you've got a reasonable distribution of blue spots across all the height and all the width of the chip. If you see a specific pattern, such that maybe all the dots in the top right-hand corner are red, then there's a problem there, and you need to do something. But again, the pipeline and the instrument are so robust that I can't remember ever actually seeing this very often myself. And if ever I did, unless the problem could be resolved because it was a pipeline problem, or the pipeline could be fixed so that it could handle that, then those calibrations almost certainly would not be certified, and you in principle will never see them. Nonetheless, there are some parameters that you can adjust that control how the wavelength calibration is done, and you can adjust those if you find you need to. So we can continue the workflow. The second wavelength calibration, looking very similar. We can simply continue. And now we come to the instrument response, the standard star observation. So here we see, oops, daisy, wrong button. So here we see the extracted spectrum without just flat fielded, but not corrected for the atmosphere or anything like that, and the response function that has been generated from it, and that will be applied to the science spectrum. Sabine, if you're there for a moment. Hello, Sabine. Come in, Sabine. Hello.
Okay.
Okay.
So again, here, I haven't been really listening until I heard my name.
Yeah. So this is what I wanted to show you, that the response function still has this kind of feature in it. So yes. Does this already indicate that it's the improved method, yes. Or?
Yes. So because what we did, formerly the UVES pipeline used Hamui data, which had a sampling of 50 angstrom bins, which is of course not really well suited to a spectrograph like UVES. What it uses now is high resolution model spectra. And of course, when you look at the strong lines in the very core of the lines, there are small mismatches in resolution. And this is why we do the same as we do for X-shooter. So we define points at which the response is integrated. I'm not sure if we integrate or we take a median. But we omit the very line core regions. So let's say what you see there, this dip and then the small emission line. This is just a small mismatch in the core of the line.
Yeah.
So we interpolate across that region.
Okay, very good. So this is already the much improved method.
Yes.
But it still has some small artifacts, but we mitigate that by interpolating
exactly
the data. Excellent. Okay, thank you very much for the clarification.
If you ever want more details, which you probably don't want, I can send you the report on what we did.
Yeah, no, it's okay. I read the reports on X-shooter and I basically know the procedure. Very good. So these small features here are perfectly normal, and as Sabine just explained, and what we're after is the nice smooth response function under there. You can actually see, perhaps, if your resolution is good enough, the points I think that Sabine was talking about, little red points that are actually used for the defining the function. And you can see that they avoid the centers of the bright lines. Okay, so a few other things. Again, we have parameters that can be adjusted, and the possibility to rerun the workflow or continue. Essentially, it's the same set of parameters as is available for the science recipe. In fact, it's exactly the same kind of processing for the two recipes. We're using much of the same code, And then there's just the extra step of determining the response function for the standard star. So we can continue on to the science spectrum. And finally, we have, so here we see the raw extracted spectrum, as it were, flat fielded. So the shape of it is determined mostly by the shape of the flat field lamps and also by the atmosphere. And then we have here the flux calibrated spectrum. I would suspect that given the way it's trailing off here at the end, at the very blue end, that the atmosphere was perhaps a little bit different at the time that the observation was made compared to the standard star. And so the bluest part of the flux the atmospheric correction, which is basically determined by the standard star, is not quite 100% there. So if you need absolutely spot on flux, absolute flux calibration, then the only way to do it is to attach standard star observations to your observations at the time. The calibration plan that is at the observatory, as I said, by default doesn't flux calibrate, but if there happen to be some health check data that correspond to your science, you'll get that, and you'll get this kind of flux calibration, which is good to maybe 10, 20% or so, depending on the wavelength you're interested in and so on.
John?
Yes.
Don't forget, if you use a narrow slit, you have slit losses. And most people with UVES use a narrow slit.
Sure. Yeah.
And of course, the slit loss increases towards the UV.
Yes. But if you use elevation mode, then the slit loss, well, increasing slit loss to the, yes, there's the various factors there. But at least you can mitigate the slit loss due to atmospheric diffraction by using the LF mode.
Yes, but let's say I'm just looking, triggered by a completely different topic on slit losses, and I'm looking at data where people observed with a wide slit and then immediately afterwards substantial slit losses.
Sorry, I lost everything you said after I'm looking at data that people observed with a
I'm
wide
looking
slit.
at data where people observed first with a wide slit and then immediately
Yes.
afterwards with a narrow slit, with a very narrow slit, admittedly, 0.5 seconds.
Yes.
And when you compare the two data, you have slit losses of about 50%.
Okay. And so you see substantial differences not only in the absolute flux level, but in the shape too.
Yes.
Is that what you're telling me?
You do.
Ah,
Yeah.
Excellent. Oh, that'll be interesting. I look forward to seeing that report.
I'm not sure. And actually, we're not talking about UVES here because UVES, I haven't found such data. I'm talking about X-shooter, but I don't think this is X-shooter specific.
No.
Nevertheless, I'll send you the report when it's in a shape to be sent around.
Great. Okay. All right. Escher, your hand is still up. Do you have a question, or is that just from the last time?
No, I raised it again. I'm sorry.
I'm sorry, I don't have any question. Yeah.
No problem. Okay. Okay, so we have reduced spectra with flux calibration with all the caveats that we just discussed. We can again continue, and again we end up back here at the product explorer. There was one other thing, well, it's another thing I want to show you at this time. So these actors with the graphical user interface have the possibility to adjust certain parameters. And then you can re-execute. But for each recipe, it's usually only a limited number of parameters, not all of the parameters that are possible in the recipe. And then maybe sometimes you need to actually adjust the parameters of one of these recipes that doesn't have a graphical user interface. That is certainly possible. It's just a little more complicated, and you cannot do it in an interactive way. Essentially, you have to, well, let me show you first how to adjust it, and then I describe. So for example, if I want to adjust one of the parameters of the science recipe that is not in one in the graphical user interface, then I have to come to here and I have to open the actor. Just do some resizing so it's a bit easier to see what's going on. Then I need to find the actor that is actually the recipe executor, which is this one with the what do you call it? A drum with a circle on it, I guess, something like that. Then if you configure that actor, then you get a list of all of the parameters that are in the recipe. There are two types here. There are these ones that have parameter name equals port, and that means it's taking the parameter value from the interactive GUI. All the others that don't have port are the ones that have been set, and they're set to typically their default values. And these are the ones that you can that you can adjust if for some reason that you need to adjust it, and it's a parameter that's not accessible via the interactive window. So if you would change something, then you would click commit. I haven't changed anything. I just press commit. You then have to go back, and you have to then run the recipe all the way through, and you'll get one shot at it. So if you adjust the parameter and it's not quite the value you need, then you have to go back through that process of adjusting it again, opening up the actor and then configuring the actor that's inside the actor, and then running the whole workflow again. So it's a lot less convenient, but it is possible, that's for sure. Okay. Yes. One last thing that I wanted to show you. Let's say let's say you're happy with your reductions and you're finished, so you close up, or perhaps you ran the workflow in non-interactive mode, which I'll show in a moment. What have I done there? I've started it again. Okay, didn't mean to do that. So what alternatively, all right, yes. But let's say, oh, I forgot, I want to check something. I want to see what my results look like again. So instead of so you can run the workflow going directly to the product explorer. So we can just do the help again, just to get to check. And it's here, this line here, where you can go directly to the product explorer. So minus E, oh, not minus D, minus E. And instead of opening up canvas, or as well as opening up the canvas, it will open up the product explorer directly. And it always just takes a minute or two. There we go, directly to the product explorer, and then from there you can explore some of the products. Get it from there. Now display the pipeline results. Here we go, and you can get back to the interactive window and again explore the spectrum as you go. If you actually zoom in close enough, you can see that it's actually plotting the result, the spectrum, and the uncertainty on the spectrum. So the fuzziness on the line is the uncertainty, the calculated uncertainty. Okay. And you can either just close the window by closing the window, or you can click any of these, continue workflow or run recipe, and it will close. It won't actually do anything because it's not being executed within the workflow, but it just closes the window. And to finish off, you can just continue, and you'll come back to the command line prompt eventually. No, Control C to exit apparently. There we go. Okay, that is more or less time up, a little bit over actually. Does anybody have any questions? Doesn't seem so. Is anybody still awake? Yes, Esha.
Yeah, I was just curious about whether MolekFit and Sky tools can be used in UVS data analysis. I mean, if I can do the modeling with
Yes,
MolekFit.
yes. The answer is yes. We have, although it's a little bit complicated just right now, we released a new version of MolekFit, this public release. So our pipeline department releases a new public release of our pipelines essentially every year in around about May. And this year, as part of that release cycle, they included a new version of MolekFit, which is now implemented as a Reflex workflow. We've actually just released yesterday, I think it was, a new version of that, which now works properly. But for the moment, it is only configured and set up in a nice way, I should say, for X-Shooter. The older version that you can still find on the ESA website, which has directly the Python user interface and so on. So you can still get that version, and that has some example files for UVES, I believe. And you can, so for UVES, it's probably still a little bit easier to use the old version, but it's, so you can certainly apply MolekFit to UVES data. And there are some examples. I mean, the best way to try to do that is to use the examples that are part of the MolekFit package and adapt them to your data. Unfortunately, that package is horrible in the sense that if one of your parameters isn't quite right, the code will crash horribly, and the error message is completely useless in terms of trying to work out what the issue may be. But at least it's a good place to start, and hopefully one can find a way. If you need to get to there, then give it a try and contact USD if you have any trouble. It may or may not be easy at this stage to adapt the Reflex workflow for MolekFit to UVES data. I haven't tried that myself. I may give that a try in the next weeks or months based on the new version of the X-Shooter workflow that's been released. But for the moment, that's where we're at. So certainly in principle, yes. In practice, right now, it's a little bit complicated.
Okay, thank you.
Okay. And if you need to do that urgently in the next weeks, months, then give it a try, I would suggest. And if you need help, just contact USD.
Okay, thanks.
Okay. Any other questions?
John?
Alessandro, yes.
I wanted to ask something which somehow is on the other side of what was just asked. Assume I have something with an object which is relatively faint, so I had to integrate a lot, and I have some cosmic rays. So one thing I could think of would be to run a program like LPO on the raw images, and then pass those images through the workflow.
Yep.
In that case, what I would imagine doing would be to rename the files so that I can separate the files, the original raw files, from the LPO run files.
Yep.
So I guess what I'm trying to ask is, can I run files with an arbitrary name, provided that they have the proper header? I'm not touching the header. And can I run these files through the pipeline? Sorry if the question is a little bit.
No problem. The question's fine. Yes, as far as I know, yes. Just don't put any spaces in the name, in the file names. And you cannot, you'll have to separate them in directories. So you won't be able to run the originals and the modified files in the same go. You have to have them in separate raw data directories. because ESO Reflex will go, oh, these two, because it actually checks the checksum. No, they have different checksums. So in fact, you can probably do it even like that. Yeah, my answer is yes. And you probably can put them all in the same directory so that you could then run the two together. Having said that, number one, optimum extraction should deal nicely in most cases with the cosmic rays because it's fitting a profile and it will ignore the blips, as it were, of the cosmic rays. So it should fit the profile to the underlying spectrum and thus correct for the cosmic ray. Depending on how many there are, this may or may not be so successful. But I mean, how long are we talking about in terms of exposures?
I'm just referring to an hypothetical case.
I mean, I think the optimum extraction should work fine as long as it's not more than 100 hours continuous, I would think, because just in terms of the cosmic ray density. However, having said that, if they are extremely low signal to noise spectra, then optimum extraction may be very difficult, and you may need to resort to the average mode extraction or another in cosmic, and therefore optimum extraction just won't work because there's not enough there to actually make a profile for. And then you have a problem because then that won't take account of the cosmic rays. So then this method would be applicable. However, what I could suggest to you as an exercise to the Reflex community, to yourself, at the last users workshop, I showed how to take the cosmic ray correction actor from the Flames UVES Reflex workflow and put it into the Force workflow. So you could do that. You could implement. You could put a cosmic ray corrector into the workflow itself.
Oh, that sounds very interesting. Okay, I'll try that. Thanks.
So there is a video that you can find. I'll see if I can find the reference to it, but there's a video online of my presentation from 2 years ago when I described exactly how to do this.
Awesome, thanks.
Okay, welcome. Any other questions? Okay, then I will let you go all your separate ways. If you think of any questions in the next day or three, don't hesitate to ask them in the UVES questions channel. And good luck with using ESO Reflex.